Hello everyone, I'm Yunsheng from UC San Diego, and I'm really glad to introduce our work for multi-source DOM adaptation task based on dynamic transfer. Multi-source DOM adaptation is a more complex DOM adaptation problem by considering source domains as a mixture of several subdomains. For multi-source DOM adaptation task, I mainly consider the dominant dataset, which contains 6 different domains with 345 classes. The setting for multi-source DOM adaptation is to train a model with 5 domains and test it with the rest one. In order to solve multi-source DOM adaptation problem, traditional methods try to align all the domain pairs together, which not only consider the domain gap exists between each source domain and the target domain, as well as the domain gap among different source domain pairs. However, this method has 2 drawbacks. First, the model is forced to generate common features among all the domains, and optimizing such a model on the images with big variation will cause domain conflict and weaken the model's discriminative capacity. Here, I show some results when the model is learned in the supervised manner on domain-net dataset to prove the previous analysis. If we train a model per domain and average the performance of each model, we get the classification accuracy as 69.1%. However, if we train a single model on all the domains together, the average accuracy is only 67.5%. When the domain alignment loss is further added to force the model to generate common features, the result is further decreased to 67.2%. It indicates that a single static model, even though as large as ResNet 1.1, can still hardly handle images with large variation, and the domain alignment loss will further weaken the model's classification capacity. The second problem is when alignment happens among source domains, the domain labels have to exist, which is not a general case in real application. Due to the existing problems, I start to think about if there is a model that can map all the source domains to a common space without causing domain conflict. In order to answer this question, dynamic model is a good choice. It is because for dynamic model, it can modify the kernels based on input samples, which avoid to apply a common filter to all inputs. With the dynamic model, one big benefit is it avoids domain conflict and replaces the domain alignment with sample alignment by adapting model's parameters according to samples. Therefore, the domain labels are no longer required. In order to implement dynamic model for multi-source DOM adaptation task, a novel model named dynamic residue transfer, which is short as DRT, is proposed in this paper. The model is composed with a static layer W0 that learns the domain common features and a dynamic residue delta W0 to represent domain-specific features. The dynamic residue is composed with several kernels weighted by the dynamic coefficients pi that are predicted based on different inputs. I hope domain alignment can be achieved by mapping samples to the common space with different coefficients. In order to test the power of the proposed DRT in dealing with domain conflict, it is applied on ResNet 1.1 and I test it on domain-net in the supervised case. Here, I train the model on all domains and report the average classification accuracy. We can find when DRT is used to adapt models, the classification accuracy on domain-net dataset is almost 2% better than the static model. It indicates that the dynamic model can significantly reduce the domain conflict without the knowledge of domain labels. Furthermore, I show the adaptation performance given by DRT when it is combined with different domain adaptation loss functions such as ADDA, MCD, and M3SDA. We can find by adapting the model's parameters, the adaptation performance is substantially boosted on all domain alignment methods. One interesting thing is, in the supervised case, DRT only improves the average performance by 2%, but when it is applied on domain adaptation problem, the margin becomes much larger. For instance, when DRT is combined with ADDA and MCD, the improvement is more than 10%. To further validate DRT on domain adaptation, it is compared to other methods which used much more complicated domain adaptation techniques. We can find by simply applying the DRT on MCD, it at least outperforms other baselines by 3%. And I hope this work can change the ways of doing domain adaptation from designing better alignment loss functions to looking for better transfer backbones. Thanks for listening.